let us start our third lecture. So, today will be our third lecture. And in last two lectures, we have talked about a material tetrahedron, and in that material tetrahedron, we have seen that it has four broad sections. One is composition or structure. Then you have properties, then processing, and finally, we have performance. And all these four segments are interconnected and we have also seen with examples that heat treatment falls in this category, which is processing of material. And this overall tetrahedron is valid for any material, and rather any material which we use in our applications. And final aim is definitely performance. In order to get performance, we need to look at properties, and in order to get properties, we need to look at composition, we need to look at structure, which could be microstructure, crystal structure, or we would see that even macrostructure becomes effective in controlling the properties. And in order to make modification in the properties as per our wish, we can also change the processing condition on the same material, and when we change the processing condition, we can have change in the structure again, correspondingly change in properties, and finally, we have different performance. And in this processing, we have heat treatment, and heat treatment is nothing but a temperature time situation. Now, we had example in case of mild steel, 0.2% mild steel, where we have seen that if you do furnace cooling with the with the door of the furnace closed, we have also seen a condition where you put up the furnace and open the door. Then another condition was you take the sample out from the furnace and place it in normal air, which will be considered as air cooling or normalizing. In all three cases, we have difference in structure, little modification in the structure, and we have changes in properties. And similarly, if we do water quenching or oil quenching after taking it to 1000 degrees Celsius and holding it for 30-40 minutes, we see that the entire structure is changing. There the crystal structure changes, even the microstructure changes, and you see a huge change in the properties. Now, in the last class also we saw that whenever we see this kind of situation, this particular entire thing also this entire thing talks about few more things which are inherent to this particular diagram, while considering while seeing those all those options, all those parameters. Now, those things are inherent like phase, and of course, when we talk about phase, we also try to see what is there in the transformation. We also see the transformation. For example, when we take the sample out from the furnace and place it in cool water, we have water quenching, and then there the phase transforms. We will see later on that austenite to martensite, that is the transformation. And if we do it furnace cooling, we will see that austenite transforms to ferrite and pearlite. So, like that we have phase and as well as transformation. Now, when we talk about phase transformation, we need to see that whether what condition that transformation would take place, or what is the driving force for the transformation. So, whenever we talk about any driving force, it talks about thermodynamics. And of course, once we see that yes, there is a driving force, but whether the transformation would actually take place or not, we need to look at the kinetics part of it. So, that means we talk about phase transformation along with thermodynamics and kinetics, and need to see what is the time and temperature condition for getting that particular phase transformation as we desire. Many a times we would see that even we do this kind of situation, we treat this kind of situation, we would finally see that some phases would appear which will not be desired. Rather, those phases would lead to some problem in application and would also adversely affect this performance. And in the last class also we took the example of mild steel, but at the same time we mentioned two more things. One was in case of alloy aluminum copper, which is popularly known as Duralumin, as well as 18-8 stainless steel. We would like to see that what exactly happens if we change the time temperature situation, and we would see that yes, there would be distinct change in the material properties as well as consequent changes in the structure, which could be microstructure or microstructure plus crystal structure both. Now, at the same time we also talked that just we touched that once we get this phase transformation, thermodynamics and kinetics, we can have overall transformation kinetics, which can be best suited in terms of a diagram, which we call it TTT diagram, which is called time, temperature, transformation diagram. And TTT diagram looks typically a kind of C curve, where this axis is T and this axis is temperature and this axis is time. And once we get this kind of information, we derive those information, and then accordingly we can decide what should be the temperature and time required to achieve a particular structure and accordingly particular property as we desire. Now, these part will come later on, but before that, since we talked about two examples and in the last class we could not complete that discussion, let us have little discussion on those two things. One is 18-8 stainless steel SS with a carbon content of 0.08 weight percent. Now, this is a special steel which is called stainless steel, as we have discussed last time, and in this steel we use the steel in the form of sheet metal. And now, in this case, if we see the microstructure look like a polygonal grains, and if we see the crystal structure, we will see that all the grains are austenite and these are the grain boundaries, Now, in this particular case, we have 18% chromium, which is 18 weight percent chromium. And if we have 18 weight percent chromium in the material, and that 18% chromium is in solution, we call it solid solution. And that solid solution is also falling in the category of substitutional solid solution. The chromium atom substitutes the base iron atom and forms a solid solution. Now, once we have 18% chromium, it reacts in the environment in the presence of oxygen. It forms chromium oxide. And this chromium oxide forms a thin layer on top of this surface, which protects the material from further corrosion. Because this oxide is highly adherent and impervious oxide. Impervious means it does not allow the oxygen or moisture to get through and come in contact with the base iron metal. So, that is what it has a stainless property. Now, if we can have little change in the processing by mistake, let us say by mistake we heat this material in the temperature range of 400 to 600 degrees Celsius, which is a kind of not very suitable temperature to heat this material within this, to heat this material, because once we heat this material, because during operation, let us say we want to weld the particular sheets, particular plate, let us say stainless steel plate of this composition. If we weld it, somehow during cooling, it has to go through that temperature range. Okay? Or sometimes when we quench it after solutionizing, we need to remove the quenching strain. So, sometimes we have to do little stress relieving operation, and during that stress relieving operation, if we heat it to this particular temperature range, there something interesting happens, some transformation happens, and that is nothing but the phase transformation. And at this particular situation, in this particular temperature zone, the chromium carbide precipitates along the grain boundaries. Along the grain boundaries, which is chromium carbide. And because this is a magic temperature for getting a very high kinetics of formation of chromium carbide along the grain boundary. Now, once we have chromium carbide along the grain boundary, now this carbon has to come from inside the body, and this chromium is also coming from this particular solid solution, and then chromium, and in the chromium carbide, the chromium percentage of the order 23%. So, now from 18 to 23 it is increasing. Now, if we see along this particular line what is the composition if we see, so composition, this is A, this is B, this is C. So, now the chromium percentage further away from this is of course 18%. Now, as we go closer to the chromium carbide, because here the chromium percentage has to increase in order to form chromium carbide. So, the chromium percentage locally around the precipitate decreases and then again go up little bit and then again decrease like this. So, this is my A point, this is my B point, this is my C point along this line. So, now you see that the chromium percentage has gone down, and it can even go down to level of 2%. Now, in order to get stainless property in 18-8 stainless steel, we need to have more than 12% chromium all the time. Now, once the chromium content reduces to 2%, something interesting happens. Along the grain boundary, we do not find chromium oxide. So, if we do not have chromium oxide along the grain boundary, which is adjacent to the chromium oxide layer, these particular zone becomes vulnerable for further corrosion. Okay? So, these zone gets corroded. So, now this, that means a thin section along the grain boundary gets corroded, and that means along the grain boundary all the time we have very high corrosion, because away from the this particular precipitate zone we have 18%. So, here we have all the chromium oxide layer, here we have chromium oxide layer. So, no problem, no corrosion takes place, but this zone is exposed. So, there corrosion happens. We will talk about this particular heat treatment more detail, but I am just saying that because of change in temperature time information or heating it to this level and holding it for some time, we can get this kind of situation. And once we get this kind of situation, this particular steel we call it sensitized, means it is subjected to intergranular corrosion. And this intergranular corrosion is extremely bad in case of stainless steel. This entire plate can break like a kind of a brittle substance, a kind of stick. Okay? It is so brittle, it can break like a chalk, it can break into herbs, and this is also called intragranular corrosion. So, that means because of temperature time information in this particular zone, we have this sensitization, and that leads to intergranular corrosion, which is not good for our performance. It damages our performance of that particular steel, and it is no longer stainless. So, that means it is not only that whenever we do processing, it would have positive effect on performance, it can also have negative effect on performance. That is why it is important to study what happens when you do processing, what happens to the phase transformation, and what happens to the final performance. So, this is one of those classic examples that structure does not change, but simple phase transformation from solute solution 18-8 stainless steel to chromium carbide formation along the grain boundary leads to intergranular corrosion. This is one example. The next example is 18-8 is duralumin, which is 2000 series alloy, and mainly aluminum copper alloy. And the best example is around 4 to 4.5 weight% copper we have in this particular system. Now, let us talk about these particular alloy in order to complete our discussion that yes, heat treatment or processing can lead to change in the properties and performance. So, that also would tell us that why it is so important to study this particular diagram, and when we study this particular diagram, we have to see synergistically, not like we can change the microstructure, it will give problem, it will solve our problem, or if we change the composition, it will solve the problem. We have to see why we have to change, and that why that answer would come if we understand this. For example, before we go into this, if we have 0.08%, but if we can reduce the carbon to 0.01%, then this sensitization problem can be avoided to a great extent. Because for the chromium carbide formation, though we have chromium, but we do not have sufficient carbon to form chromium carbide. Okay? So, that is a possibility. Or we can also add little bit of niobium or niobium. So, that niobium will take care of this carbon, because niobium has a higher carbon affinity. So, niobium would form niobium carbide, but it would not allow the chromium carbide to form. And interestingly, the stainless property comes from the solute solution of chromium presence of the order of 18%. So, that suggests that if we add little bit of niobium, this can avoid this sensitization. So, these kind of things we can be able to know if we understand this particular diagram. And finally, we need to also understand why we need to do the heat treatment. Now, coming to duralumin, in order to understand duralumin, we need to see the phase diagram, and let me draw the aluminum copper phase diagram, or the part of that particular phase diagram. Now, this is whenever we draw phase diagram, it is a binary phase diagram. This axis is temperature and this axis is percentage copper. And if we see that this temperature is eutectic temperature, which is 548 degrees Celsius. Now, here we have this kind of situation, a terminal solid solubility, and we have eutectic system, and this is almost about close to 30 copper, and then this is theta phase, which is nothing but, and the rest of the part I am not drawing, because this part would be important for us. And here this section we have theta, which is nothing but aluminum Cu2, sorry, aluminum 2Cu. And in this case, this particular section is almost about 5%, roughly 5%, and this zone is alpha, this is alpha plus liquid, and this is theta plus liquid, and this is liquid. And in this zone we have alpha plus theta. So, if it is in equilibrium, that time this would be the phases we can arrive at different temperatures. Now, we have something like this composition, let us say we take this composition. If we take this composition, then at this temperature the normal phases would be alpha plus theta, fine, and this theta is the second phase, and the second phase would give me little bit of hardening. But the problem would arrive that this theta will not be able to increase the strength to a great extent. But if we do a little bit of change in the processing, we can have a huge difference. Now, what would be the processing difference? Now, if we, let us say I have some particular thing, this is room temperature, let us say, let us assume that this is the room temperature, and at this temperature whatever phase mixtures what we have, if we take it to this level, and at this level if we hold it, everything will mix, and whenever everything mixes, okay, and that time it forms a single phase alpha, which is nothing but solid solution aluminum, solid solution of copper in FCC aluminum. Now, solid solution of copper in FCC aluminum, that means here if we hold for some time, then it forms complete solid solution. So, that means all the theta phase, which is the second phase Al2Cu, that phase will dissolve and form a single phase. Now, after that, if we quench it quickly to a room temperature, we will have little increase in hardness, because quenching leads those entrapped copper in the solution, but at this temperature we do not, that system does not like to hold that particular amount of copper, excess copper. So, this is my excess copper, this is my excess copper, and actual equilibrium percentage of copper in solution is this one. Now, so that means what happens to this excess copper? And this excess copper at room temperature, it takes years to come out from the system and forms a fine precipitates. But if we somehow increase the temperature to about 200 degrees Celsius and hold it, and because of increase in temperature, we accelerate the copper coming out from the solid solution and forming fine precipitates. And that time the precipitation does not happen directly to this, rather it goes through several phases, which starts from GP zone, which is Gaynor-Preston zone, to theta double prime, to theta prime, and finally equilibrium theta phase. Okay. So, now once we have this kind of situation, the hardness increases to a great extent, and that time we call it precipitation hardening. And the hardness response, if we see the hardness, and this is my time. Why time? Because what I am doing, I am quenching it, I am making it a solutionized aluminum copper solution and solid solution, and then I am heating it to 200 degrees Celsius, and as a function of time I am seeing the response of in the form of hardness. And hardness is what? Resistance of the material against penetration and the penetration of the indents. Now, if we measure the hardness, we will see the hardness plot looks like this. So, that means this is my solid solution, okay? And then gradually we have GP zone, theta double prime, theta prime, and finally theta. So, the hardness increases greatly, and this particular thing happens at 200 degrees Celsius if we hold it, and this entire process we call it age hardening. We call it age hardening. So, now if we come back and see what actually we did nothing but a change in processing, which is the heat treatment, and heat treatment is nothing but change in processing temperature and time. And here we solutionized, quenched, taken it to little higher temperature, held the sample, and then measured the hardness, and we are getting this response. This is called age hardening, and this age hardening is coming from precipitation hardening mechanism. Precipitation hardening. So, that means here we are fixing the composition, but we are changing the structure, both the structure, because whenever we have these changes, we are changing the crystal structure, okay? And then finally also we are changing the microstructure, because the microstructure would look like, if those are the grains of FCC aluminum, which is alpha phase, those precipitates would appear as small precipitates, and these precipitates would not allow those dislocations to move freely, because those precipitates would hinder the dislocation movement, and whenever we have dislocation movement is hindered, we have increase in hardness. That means the more strength is required to cross that barrier, okay? And that is what we get, increase in hardness. So, this is a typical age hardening, which is coming due to heat treatment, due to processing. So, that means heat treatment is extremely important, and we need to look at this heat treatment very carefully. And in the next section onwards, next lecture onwards, we would get to the phase transformation, thermodynamics and kinetics, and this entire 20-hour lecture will be concentrating on the fundamentals behind heat treatment, rather than looking at you take the sample to some temperature, hold it, and then take it out and see what is the performance, but rather why we should take it to that temperature, when we should take it to that temperature, how long we should hold the temperature sample. Those information, those answering of those questions, why, how, what, when, that would give idea about heat treatment, and that one will concentrate, will talk about in this particular whole 20-hour lecture. Thank you. So, we will continue in our next lecture. Thanks.